You ready? So hi everyone, and welcome to the second Stay-at-Home Polymer webinar. Today, Carlos Guerrero Sanchez will be presenting about high-throughput output techniques for polymer synthesis. Carlos studied chemical engineering in Mexico and then led the combinatorial chemistry lab at AUL. And subsequently, he earned a PhD degree in combinatorial materials research and polymer science at Eindhoven University of Technology and founded Ionica Technologies, which is working on the commercialization of ionic liquid-based smart materials and catalysts for polymer recycling. He then worked for CSIRO in Australia in 2009 to 2013, which is where I met him, in high-throughput experimentation and RAFT technology, and he's currently a research group leader at the Friedrich Schiller University in Jena, and working in the laboratory that's led by Ulrich Schubert. And so with that, I'm very happy to introduce Carlos, and the floor is yours, Carlos.
Well, thanks, Simon, for the invitation, and also thanks to Etienne. I must say this is the first time I give a webinar online, well, a webinar. And well, let's see how it goes. No? So basically, I will be talking about high throughput and output techniques for polymer synthesis. And well, as an introduction, I can say that these techniques are just experimental techniques with the goal to speed up your research or the synthesis of polymers in such a way that you can have systematic variations of properties or molar masses or functionalities. And you can investigate all these arrays of polymers in a more structured way to try to find more easily some trends or properties or hits in a collection of polymers, right? So basically, the main motivation for using these techniques, which are very used in other fields of chemistry, for instance, in the pharma industry, are basically just to speed up the research and automate the work and make through parallelization and the use of some robots. In such a way, you can achieve more experiments at a given time with less people or less effort, let's say, and you can explore more the parameter space in terms of to investigate different effects or reaction conditions or concentrations, solvents, etc. So basically, this is the motivation behind this, the use of these techniques. When you think about a polymerization reactor, it can be very complex system, basically. I choose this example, for instance, this suspension polymerization is, I like very much these kind of reactions because they are very challenging. So you have all sort of effects and phenomena going on there. So basically, you have a solid phase suspended in a liquid phase, and you have to keep it in such a specific conditions to have a good equilibrium between the physical phases and the chemical reaction going on. And at the end, well, basically, you get a nice polymer beads or pearls that you can easily separate it and get your material ready to use with some filtration and some drying. But in such a system, of course, there are a lot of things or variables affecting the reaction. Of course, temperature, concentration, solvent, type of initiator, additives to keep the phases stable. The speed of stirring or mixing is, of course, a big challenge to keep all this. I did myself one of these experiments in the past, and well, you are careful enough, you end up with a chunk of polymer in the bottom of the reactor, and it's not nice for sure. And the use of combinatorial or high throughput techniques is basically help to optimize this kind of systems or investigate the effects of all these reactions or variables in the reaction. And you can systematically find trends, how the different variables are moving up and down on a certain property. And moving on, well, basically, the main goal is to speed up the research. No? In a normal basis, if you are a good synthetic or polysynthetic polymer chemist, you can achieve maybe 1 or 2 of these reactions a day. But through automation and parallelization, well, you can just number up the number of reactors, and the limit is, of course, your budget, how many reactors of these you can set up, and how many of the polymers produced you can handle to characterize them. So that's the whole idea. Just number up the reactors, and also try to use some automation to fit some chemicals, or to take out some samples, or to characterize the systems in online, situ, or offline later on. Well, as I said, in normal conditions with a chemist or 1 or 2 chemists, you can achieve maybe 1, 2, 3 reactions per day. But sometimes it's not enough data to find some trends or optimal conditions, and determine a reaction. So that's why people start to look at automation already for 20, 30 years ago, especially in the pharma. It was successful at some extent, but of course, these techniques are still developing, and it has some limitations, as you will see later on. But all in all, the goal is to increase efficiency, to perform faster R&D, to generate knowledge more rapidly, and discover trends, and perhaps optimize some systems, some reactions or properties of materials. Well, this automation and parallelization is definitely not new. Well, over 200 years ago, many chemists or scientists start to think about this concept, how to cover more work in a certain time. And as you can see in these pictures, very old equipment, how people in the past used to do this kind of things. There are even, well, at that time there were patents on this equipment. And nowadays some companies are recycling the same patents, but of course sometimes it's harder to patent just a number of reactors. No, they have to come up with some automation or different couplings or online measurements to be more innovative. And well, but where do we start if you want to do high throughput or high output experimentation in polymer science? As I said, for the pharma industry was somehow more successful or so far than for the polymer field. And the reason is that in the pharma or small molecules chemistry, the molecules are more easily to handle, no? In solution or on different phases. But when you come to a polymer, you encounter a different kind of problems, no? Higher viscosities, heterogeneous systems, because you have different polymer lengths, chain lengths, and that creates a lot more complications. No? But well, it's been demonstrated in the past that people or chemists are really clever persons, and they start to somehow speed up the number of reactions to achieve more results in a certain time. So, and I give you a couple of examples here. You don't need to have very fancy equipment or very fancy robots to start to do some high throughput experimentation. So, well, very recently people have even published these kind of works. They take microtight plates to systematically make variations, no, along different conditions or concentrations along the plate, and achieve a library of materials. No? Of course, the volume in here will be limited to the size of the wells. Normally, it's 250 microliters, depends on the size. But you can even go smaller, no, to a few microliters. In these examples, for instance, from Australia, from a group of Professor Boyer and his colleagues, they show different arrangements to perform RAFT polymerization. For instance, they make a library of different polymers. Sorry, I need to go back. A library of different acrylates or metacrylates, and with different techniques, with RAFT technique or UV photochemistry, for instance. they make combination of polymer-induced self-assembly polymerizations, and but it's been demonstrated that they can generate a lot of materials, right, in this sense. But the problem here is that the size. No, if you need let's say certain amount of polymers, you need to scale up somehow these techniques. They're okay for a quick screening, or you obtain a quick answer, yes or no, in certain properties. But to investigate in more detail or to optimize some conditions, you need to have a larger scale. So this is just to give you a sense of how you could start in a very simple way to make these kind of techniques. No? So normally, well, you don't have a pipetting robot or automated liquid handling. You can just pipe it by hand to different wells and vary solvents or monomers or initiators or RAFT agents or ATP chain transfer of different things. No? Of course, many polymerizations are oxygen sensitive, or some of them are even moisture sensitive. You need to come up with a good idea how to degas all these wells to achieve a proper polymerization. And in this example, on the top, on the right top, you can see that this research used an enzyme based on glucose that to achieve the removal of oxygen. So it was a nice work. So basically, they can work with these microtight plates and open base, no? So connected to the normal atmosphere, and still the polymerization will work. Well, in a similar way, well, you can see in this picture, the other use photochemistry to make polymers. They vary monomers, different concentrations to achieve different molar mass or different block of polymers, for instance. It's a very simple way to start into the field. Some other researchers propose these PCR tubes in a similar fashion. Basically, here you can number up the unlimited tubes, no? And you can achieve very good libraries and achieve different combinations of monomers or reactions and additives or solvents and initiators. Well, that's okay if you have good skills how to handle pipettes by hand, or how to fill up a lot of small tubes by hand. It's okay, but then of course you start to look motivation when you have to fill up 96 wells with 4 or 5 chemicals. Might be a lot of work, no, and repetitive work. So that's why people start to introduce some robots or robotics to make different combinations of reaction mixtures or solvents or compounds. And so basically the idea here is that if you take the same microtight plates or same PCR tubes and you combine it with a pipetting robot, that will save you a lot of work, but also probably you will increase accuracy or precision, because of course if you do it by hand after the 10 or 20th tube, you start to lose motivation and perhaps to do some mistakes in the dispensing of the different compounds, right? So that's why people start to look at robots and how to combine not only microtight plates or PCR tubes, but different kind of vessels to either to prepare reaction mixtures or to run the reactions in situ. Right? So yeah, these kind of robots, let's say, is what depends on the budget available, but nowadays they are not so expensive and they are rather easily accessible. So that would be, let's say, the second level, how to start to do a high throughput experimentation in polymer science by a combination of these plates or different vessels or vials with a simple pipetting robot. So people show some nice examples here in this slide. But then, of course, some companies start to realize about the potential of these new techniques and a good market in chemistry. I start to build up different versions of synthesizers and parallel synthesizers and combine it with some pipetting robots. Here is one, probably, if I'm not wrong, is one of the first commercially available synthesizers from the company Chemspeed. I must say I will be talking about a lot about Chemspeed because, well, we collaborate very closely with them, and also, in my opinion, they have some of the most reliable machines in the market. No? That you can achieve more things with these kind of machines in comparison to other commercially available platforms. But of course, I will also show you that there are some limitations, even though you have a fancy robot in your lab, you still have to be critical and wonder what if it makes sense what you are doing. But talking about this first commercially available platform, it was nice. I did my PhD in one of those, basically, almost 15, 20 years ago. I will tell you more about it later on. And basically, what you can do is liquid reactions or to some extent some solid phase synthesis in jacketed reactors that you have this. It's an array of different numbers of reactors that you have the same temperature control. Some versions come with pressurized reactors for olefins or other reactions, for instance, hydrogenations and so on. You can put all this platform in a hood, so you can achieve certain level of inner atmosphere in case your chemistry requires. You can do some separation or some basic separations of your compounds once you finish with the reactions. So you can do some extractions, liquid-liquid extractions, for instance, or filtration, evaporations, crystallizations. And you can couple with some analytical equipment, for instance, like gas chromatography to measure monomer conversion, or size exclusion chromatography for molar masses. Right? They're sort of compact and they were very handy, but after some years, the company stopped to producing it and they migrate to newer versions that you will see later on in the presentation. They still serve these platforms, but they don't sell it anymore. They just maintain the customers when there's some troubles to keep these machines running. I tell you a bit more details about the reactors that are available, and actually we currently have in our labs here in Jena, and the ones I'm more familiar with. So basically, most of my research we perform it in these kind of vessels. As you can see here in the pictures or in the diagrams, is an array of different reactors. In this case, in the left side, you can see up to 8 reactors. So you can set up reactions of 20 milliliters. In the right-hand side, you have an array of 16 reactors of 7.5 milliliters reaction volume. They have a jacket, so basically you can keep or control the temperature through these tubings that they are connected to a recirculator, basically. So you have the same temperature in all the reactors. If you want to vary the temperature, then you need to set up a different experiment. But let's say, on the other hand, you can vary different properties inside the reactors, like concentrations or other variables. Right? On top, you can see some condensers that they are also connected to a recirculator that is cold. So that allows you to work at reflux conditions, no, in case it's necessary, and avoid evaporations of the solvents or compounds. As you can see here, in the right-hand side, you see different tools on top of the reactors. That well, these reactors are covered by a block or lid that you can open it and close it individually and put compounds inside the reactor, so take samples at different stages of the reaction. You couple it with a robotic liquid handle that I show you later on how it looks like. And these robotics can pick up different tools. For instance, these liquid handle systems that you can aspirate reagents somewhere else in the deck of the machine and bring it to the reactors. No? Likewise, you can also pick up solids which are contained in these small cartridges and dispense different amounts into the vessels, right? Different combinations. So basically, you can prepare your reaction mixtures once the cocktail is ready. So you fire up the temperature and start the polymerization. Likewise, you can take samples during the course of the polymerization, of course, to follow up the reaction and measure some kinetics, or simple to get access to those materials or intermediate materials. Moving on, well, here I summarized some of the features, but of course, nowadays they have more devices and accessories that you can combine or make use in different researches or projects, right? Chemspeed is not the only company, of course. They have some competitors like Meted Solid or CIMIX in the past. They don't exist anymore, or not as a CIMIX itself, Redleys, and some other companies, no, that they produce parallel reactor vessels and coupled somehow into a platform. But in this case, you have well, different arrays, as I said, of different reactors, different sizes. Depends on the volumes. It depends on the capabilities of the recirculator. You can achieve temperatures below well below 0 degrees, minus 90 in this case, to 140 or even 200 degrees. No? So it covers a broad range of temperatures to make different kind of polymerizations or even other reactions. No? So you have different types of reactors, like here individual heating reactors. In this case, in the very right side, you see the glass arrays. This is only one temperature for the whole array. In the middle, you can see individual heating reactors. That means you control the reactor individually, and you have a sensor for each vessel. So basically, you have more capabilities in this case. And just about the middle of the screen, you can see also microwave tubes. So it's also possible to combine it with microwave reactors and perform the polymerizations in a microwave fashion. And the companies have developed different tools, very useful tools to handle different kind of substances or to transport vials from one side to another side of the decks. For example, here I show you the liquid, the solid dispensing units in the very left side. Then comes the liquid handling with up to 4 needles. Nowadays they have up to 8 needles, for instance. So you can go more faster to dispense different liquids. An homogenizer in case you need something which is very challenging to dissolve. Ultrasonic probe, for instance, microtactile plates that can be transported or filled up with different samples or solvents. A barcode reader to keep up control of the different substances and experiments, right? All in all, I mean, they are very versatile machines, but of course, sometimes not everything goes so smoothly, and there are limitations as well, right? Here you can see a typical, some typical pictures of how a deck in this kind of platforms looks like. Here on the very left, you can see the robotic arm that is holding the liquid handle tool. And this liquid handle tool can basically aspirate some reagents here, put it in the reactor, which is under inner atmospheres or different conditions. With the reflux and the reactors on the bottom, you can start your polymerizations. So likewise, you can take samples and put it in the different racks with different kind of tubes or vials. As you can see here, some vials with caps, 2 milliliters, some filtration devices in case you need to filtrate your polymer sample, some NMR tubes to achieve some analysis later on. And basically you can put any kind of vials, provided you have the right rack and you make the right modifications to the software and the hardware in the platform. So they are very versatile in this sense. And well, people, of course, they have coupled these synthetic platforms with different third-party devices to increase power in the research and the experimentation. You can couple it with different analytical instruments. For instance, here a UV plate reader. So basically, you make your polymerization in the robotic platform, fill up the microtighted plate, and then bring it to these kind of machines to read the different spectra. Right? Like, in a similar way, the SEC, you fill up your vials, SEC vials, and bring it to the machine to characterize it when your experiment is finished. DSC, NMR tubes, of course, you can fill it up and analyze later on once your experiment is finished. Other type of reactors that are also considered as a high throughput or high output is the flow chemistry reactors. They are not only used for polymerizations, but also for other chemistries. Some commercially available versions, you can see it here in the pictures. And on the top, of course, people have also developed high throughput techniques and different holders or adapters to even perform synchrotron experiments. No, you prepare the samples in the synthetic platforms and bring it to this kind of advanced characterization platforms. But yeah, then as an introduction, I think was okay. I will tell you a little bit about the limitations and how reliable these machines are, or what you have to look at when doing these kind of experiments. Of course, if you put garbage, you will get garbage out, of course, and a lot of garbage sometimes. Right? So first things you have to ask yourself when you do an experiment in these kind of platforms, or I would say in any machine, no? How reproducible is your experiment, no? Or how precise is what you are doing? So in that sense, high throughput experimentation must be can be precise. So it's a requirement because, of course, you are not able to reproduce your experiments. It's not good. Or basically, if you are not sure that it's not accurate, of course, the results you will get will lead you to false conclusions or mistakes in the data. So basically, as you can see in the small pictures here, reproducible means even though maybe it's not precise, but it's still what you put every time, you get the same thing. That's something very important. Even let's say it's perhaps far of the reality, or let's say far from on the way you normally do the experiment in the hood, in a conventional rhombor or flask, for instance, might be different than the synthesizer, but it's already a good step if it's precise. That means that the results you get while using the same conditions and the same chemistries are the same, right, all the time. That's precision. And you can also be accurate under certain conditions and certain chemistry. That means you can have a good precision that all what you put all the time should be the same, let's say, but also is very comparable to what you do normally in the lab or in the normal chrome bottom flask in the hoods, right? So it can be both precise and also accurate. Of course, if you have both, it's even better, right? But sometimes it's just hard to have both things in these kind of platforms, and then you have to figure out how to find a good balance what you can live with, right? Back on my days of PhD students, I was quite involved in anionic polymerization, and my task was to implement or to do anionic polymerization in these kind of platforms. If you are familiar with the technique, anionic polymerization is very sensitive to oxygen and moisture. So basically, you have to be very careful with any contamination. Any small contamination of water or oxygen will kill your initiator, and of course, your reaction will not proceed in a normal way or a desirable way. So my first attempt of this experiment was basically very frustrating, because I spent several hours or even days purifying monomers, solvents, and initiators, and everything so clean. Once you put it in the robot, you start to mix the different substances, and then the polymerization simply doesn't work. So after many tries and many experiments and many modifications and additions and method development, basically experimental development, we basically figure out that the parallel reactors, the glass reactors you see in the picture, they have different levels of contamination, right? So basically, you have to clean it very homogeneously before starting any experimentations. Otherwise, you end up with different molar masses or different properties, even though you put the same chemicals. So, and we come up with a solution that we kill basically all the impurities with the initiator at the beginning. So we rinse the different vessels with initiator to kill all the impurities. After some time, we take out this solution, we rinse with new solvents or distilled solvent or dry solvent, put it into the wave this solution, and at the end we achieve, let's say, somehow clean reactors, right? Once you have or you make sure that the reactions are properly conditioned to make the chemistry you want, you can proceed with the experiment in a more reliable way. So in that sense, we test the machine, and of course we check for reproducibility of the experiments, as you can see here in the SEC traces. We took different reactors, in this case 3 reactors. We put the same chemicals, same conditions, same temperature, same reaction time, etc. So basically you have to obtain somehow the same polymer. So we did that, so the results were very encouraging. So we got it reproducible at least for this technique. So we achieved the polymer we were targeting, and with a very good reproducibility in this case. So from this point onwards, we were more confident to use this machine, especially for this kind of polymerization. And we were the start to make some investigations. No? So the robot resulted very handy to measure kinetics. As you can see, you can fill up to 6, 7, 10, 20 reactors, the different conditions, and then you start to take samples at different times and measure monomer conversion or molar mass. No? So you can easily optimize or to measure the kinetics of the different polymerizations. So that was nice. We published some of these achievements, and later on, well, of course, we decided to complicate a little bit more the things. We pushed the machine to the limits. Basically, we're testing this machine, how far you can go in terms of polymer synthesis. Following with the same technique, anionic polymerization, we decided to make some block polymers. For instance, you can see here in the slide, anionic polymerization is a nice technique to build block polymer, because basically under the good conditions of inertization, you can the polymer is always living, you know, so you can keep adding different monomers and grow up some block polymers, right? So we pick up this example because then you have to go very low in temperature. So we wanted to test the machine somehow, how far you can go, and so on. So basically, the first step of the reaction was to build a block of polystyrene with cyclohexene, and 50 degrees, 45 minutes, you have 100% conversion of the monomer, and all the polymer chains are leaving. So basically, you can add a second monomer and grow a block of copolymer. That was somehow a normal step, but then you have to decap it with something called diphenylethylene to lower the reactivity of the anion and be able to incorporate the second block, in this case MMA. But once you incorporate the second monomer, I mean, it's very reactive, the system. So you have to lower down the temperature quite low. No? In the literature, it's reported to -78, no? Because they use this acetal bata. But in this case, we set up the machine. I must say we were very much to the limit, because the recirculator goes to -90. It took us a couple of minutes or perhaps hours to reach the temperature. And while you could also see that our inner atmosphere inside the platinum was not completely dry, so you could see some condensation outside the reactor. Inside, I believe it was good, because we achieved some block of polymers. Basically, didn't kill anything. But you can see in the pictures, no? You can build up different libraries of different lengths and compositions of the blocks. That was nice, but I must say we were very much to the limit of the machine. But with that, we went back to, let's say, to more normal systems, more normal temperatures, and we built up different libraries of block of polymers. No? For instance, here I show you small library of polystyrene, polyisoprene. All this is mainly done at room temperature. So it's very, very easy chemistry once you have the right conditions of the purity of the compounds on the reactors. So you can achieve basically many combinations of these and build a nice library for different purposes. At least some variations in this regard. So basically, we build up another library of something is called super polystyrene in the same platform. In this case, you combine styrene with diphenylethylene, so you achieve a very rigid part or very rigid polymer that has a higher Tg than the normal polystyrene, and then we combine it with isoprene. So basically, we got a nice block of polymer with a very soft part, very soft block, and a very hard block. And of course, it was interesting for us to investigate different properties. As you can see here, the differences in Tg between one of the blocks and the other one. It's more than 100 degrees in each case. I guess might find some applications in the tire industry, this kind of materials, right? But even though the diphenylethylene is a very expensive monomer, I must say. The viscosities were good and or low, and that gives some indications that we have good control on the platform, on the robot. While we investigate all these materials we generate by different techniques, we build up some micelles. Depending on the solvent you select, some the isoprene part might be part of the core of the micelle or the corona, depends on the solvent, as I said. We measure some DLS to investigate the properties of these micelles, and we managed to correlate all the experimental data we get with some theoretical models for micelles. Basically, there were some good correlations, as you can see in these plots. We measured the different parameters of the micelles, and they were correlating good to the theoretical models. That was nice. Another example on this anionic polymerization in these robots. You can see here some functionalizations. It's similar chemistry as before. You start with an ionic polymer, so you cap it with ethylene, the diphenylethylene to lower the reactivity, and then in the third step you introduce a functional group, in this case a terpene. This was a very nice example, for instance, because you can easily see the changes in color in the reactions. The living polystyrene is typically orange, yellow, depends on the concentrations. Once you add the diphenylethylene becomes red, very like blood basically. And once you add the terpene, it becomes blue, immediately it changes. And it's a good indication that your reaction is working and you have the good conditions inside the reactor. Well, with this kind of block or functionalized block of polymers, you can build up some complexes, as shown here. You have two different polymers with the same functional group. You can couple it via the terpene and a metal, and you also build some interesting materials. And then switching gears to a different polymerization or technique. We did a lot of RAFT, even together with Simon back in Australia, and nowadays we also do a lot of RAFT. And ionic polymerization was nice, but as I said, it's quite demanding, and it requires still some time, even with the robots, to achieve some results. So we switched to RAFT because it's a very more versatile or more robust technique, I must say, towards different impurities and functional groups in the monomers or solvents and so on. But it has, let's say, one disadvantage, if you want to call it like that. RAFT polymerization is also sensitive to oxygen. So basically, you need to make sure to remove the oxygen from the system to start to do the polymerization. Some people in the past already combined RAFT polymerization with these platforms, these parallel or automated parallel platforms. And the way they did it is basically just introduce the reaction mixture and then a needle with connected with some nitrogen or argon. So they gas it by sparking the gas for some minutes, and then you remove the oxygen. And well, it works, let's say, pretty good. Maybe it's not very strict inner atmosphere, but for practical purposes, I must say, you get the polymers you're looking for most of the time. But well, we decided to implement a different method in these machines in a similar way to an ionic. So basically, we wanted to mimic what real chemists do in the lab, and they use ampoules with the seal it with the flame to have a real inner atmosphere, or well, let's say to remove very carefully the oxygen in the polymerization. So we wanted to mimic that, and what we did is basically we lower the temperature once the polymerization or reaction mixture was inside. We lower the temperature until the mixture freezes, and then we apply vacuum. So basically, you can also apply vacuum with this machine and remove oxygen. So of course, then we melted this solid, and you sometimes you see how the oxygen start to bubble. Of course, the advantage is that in a conventional way, you seal your ampoule one by one. It can take you a lot of time to prepare some ampoules. But with a synthesizer, basically you can do it up to 16 reactors. Now, in this case, in the picture, that gives you or saves you 16 times the amount of work with the flame ampoules. Right? And we tested this method. Some of my colleagues back in CSIRO, they prepare a reaction mixture. They degas it with the freeze pump method, the conventional one, with ampoules, and I use the same mixture to put in the chemist pit and apply this method. At the end of the day, well, we got very similar results. No? He put his ampoules in the oil bath, and I ran the chemist pit at the same temperature. Let's say reaction times were similar. There's some differences because in the chemist pit you start from room temperature, let's say, to heat up your reactor up to 50, 60, 70 degrees, depends on the reaction temperature. And with the ampoules you preheat the bath, no, the oil bath, and just put it directly once it's hot. So there are some differences in that sense. But I must say they were very comparable. For similar reaction times, we got very similar conversions and molar mass. So that's an example of, let's say, precision and accuracy of the machines, right? So we're very happy with these results, and well, we tested the reproducibility of this freeze pump in the method in the chemistry, and you can see here in the plots how reproducible are. So we managed three different experiments with 3 repetitions, and every experiment we got very similar results to the different reactors. Right? So we're happy with that, and then we start to do a lot of kinetic investigations and optimization of reaction conditions. We normally prepare our experiments in these kind of Excel files. You listed, let's say, 16 reactors. That is the typical block for the machine, and you can make many variations of conditions or concentrations in the Excel file. The Excel file basically calculates all the amounts of chemicals you have to put in every reactor. With this information, you bring it to the software of the platform, fill it up, set up your chemicals in the stock solution rack, and well, come back later for your samples or your results, right? As you can see here in the pictures, once the reaction or during the reaction, the machine is able to take samples to measure conversion by NMR in this case, and take samples also for the ACC with some filtrations, for instance. So you are limited. You can get one sample every 2 minutes if you would like, because it's the time it takes the robot to pick up the tool, bring it to the reactor, take the sample, and put it in the bag. So every 2 minutes you can have a sample. Of course, sometimes it's just too much information. You need to think about not to generate too many samples, but the amount that it makes sense to learn something about your experiment. But easily in a kinetic investigation, we take or we generate up to 100 samples for NMR. Similar number for SECs. No? With that, we can measure reactivity ratios of different kinetic parameters, like I showed you in this example. This one we did it with Simon together. So we were very interested to see the system of methyl acrylate with vinyl acetate with controlled by a Santi. And this system is interesting because the two monomers have very different reactivity ratios, and you achieve sort of a block of polymer in a single pot, right? So we're interested to learn more about the parameters and the conditions of how to polymerize this system. And we set up the experiment in the robot, make a lot of measurements in terms of conversion and molar mass. We plotted, and you can see here the results. And well, Simon has some lots of experience in some programming to calculate reactivity ratios using different models. Basically, I provide to him the experimental data of the kinetics, and he come up with some numbers of the copolymerization system, which, let's say, they were really or close to the reported ones by other workers. Right? So these systems are very handy, basically, to achieve this kind of investigations. Of course, at the end, you get the polymers, and if you're interested in measured properties or use it for some applications, you can also do it. But moving on, I was also very interested at that time to build block of polymers, let's say in a fast way or in a lazy way. Once via RAFT, once you want to build up a block of polymer by RAFT, first you start with the first block, you bring it to, let's say, 60, 70, perhaps 80% conversion to avoid that many chains are dead. Then you want the second, then you purify somehow this polymer. You have to precipitate it or dialyze it to remove the excess of the polymer or the monomer, a reacted monomer. And then once it's dry, you redissolve it again in a suitable solvent, add the second monomer, and bring your second block. Then you get a block of polymer. But of course, as I mentioned, it's a lot of work to do a block of polymer in this way. We wanted to speed up this, basically. So we came up with some ideas how to avoid this purification step in between, right? And have a good balance between high conversion and still enough living chains to achieve the chain extension of the polymer. So with the chemistry, we did a lot of optimization basically in different systems, in particular this one. So butyl acrylate, we bring it to 80%, 70% conversion. And then once it's finished at this stage, we just add the second monomer to the same pot. And let's say in excess or in different concentrations, you can see it here in the scheme. So you build up the macro RAFT agent with the first monomer. And then at the end of this reaction, you have the polymer and some monomer left. So then you add the second monomer, and you obtain basically a sort of we call it quasi-block of polymer, right? A pure block, which is in red here, and a second block that might have some defects or reg defects in the black block, basically. So we were very interested to have a look at these materials. Of course, the SECD traces show you that nice shifting in the molar mass as you extend the chain, basically. But of course, we want to know how these materials behave. No? But let's say with this technique in place, you can think about so many combinations of different block lengths and monomers as well. Right? So a typical example we publish, for instance, so you start with 3 different macro RAFT agents in 3 different reactors, for instance, different lengths. Once you finish the first part of the polymerization, you distribute this original solution in new reactors, let's say at the same volume. So you end up with these 4 or 5 different macro RAFT agents, and then you add the second monomer, right, at different concentrations. That means you will achieve different chain extensions or lengths in the polymers. And of course, you can vary the conditions to achieve big libraries of local polymers in this case. For instance, here I show you three precursors of different molar masses, 7,000, 12,000, 18,000. Once you finish with the first step, you distribute in the machine automatically the original solutions, put second monomer, and it chain extend the system, right? So you end up with a nice library of different compositions and molar masses. And of course, we investigate a little bit more the properties of these different polymers by NMR. We determine the composition of each block, basically. And of course, by NMR, we also investigate how many defects is in the second block. No? If you remember, the butyl methacrylate in this case is somehow copolymerized with MMA in the second block. No? But since the amount of butyl methacrylate is significantly less in the second reaction on the chain extension, you expect that the PMA or the butyl methacrylate is incorporated in the second block to a very little amount, as you can see in the NMR. In the worst case experiment of this series, we got up to 15% of PMA in the PMMA block. But you can further optimize this, of course, with some patience and some time. You can further optimize the system. But anyway, we publish this, so we also measure DSC of these quasi-block polymers to determine if they would behave very similar to a pure block made by conventional way. And they did. Well, we found 2 TGs typical for a block polymer, right? 1 TG that corresponds to the butyl methacrylate around 9 degrees. And let's say in the defected block, which in principle should be pure MMA, but in this case has some defects of BMA, we got a TG of 101 degrees, which is also very close to the MMA. That means that even though it has some defects, the second block still behaves pretty much like a pure block for this specific case, at least. Well, you can do some other variations with the same approach. Not let's say you start with a big reactor inside the platform of the synthesizer. You just fill up your first block with some, in this case, BMA again. Once you finish, you put a lot of monomer inside in the same pot, and then you start again the chain extension reactions. But in this case, you can take samples at different times. Also, basically, you scan the whole or a broad range of molar masses. In this case, of course, depends how much material you need. You need to procure enough samples during the reaction. So we measure kinetics in this case, and you can even vary the temperature along the polymerization to speed up the reaction. For instance, in this case, we start at 85 degrees, goes sort of slow. So at intermediate conversions, then we speed up to 100 degrees, still good control, good dispersity somehow. And at the end of the polymerization, we just fire up at 215 in this case to almost bring to exhaust the monomer. So basically, the message is that you can do a lot of variation of combinations with this kind of techniques, which it would take you probably a lot of time if you do it in the conventional way in the labs. But well, switching gears a little bit, so far I have been telling you something about solution polymerization. That means you perform your polymerizations in an ice solvent, which is your polymer is fully soluble. It's the case of anionic, and many times the case of RAFT. Of course, RAFT has some variations in terms of you can do it via emulsion or other methods. But once the platform I show you is very suitable for low viscosity or solution chemistry, very handy, very efficient, very nice. But once you start to investigate different polymerization methods, you need to definitely more specialized equipment, like I show you in these pictures. So there are some process research reactors commercially available. Of course, the investment increases significantly in these kind of machines because there are more well, engineered reactors made of steel. They support pressures up to 100 bar. You can have some feedings, some pumps for adding different chemicals along the polymerization. You can combine it with the different tools to dispense liquids or solids as well in the reactors. You can open, close it. You have a real mechanical steering. In the previous case was always achieved by a vortex. In this case, you have a real impeller that provides the good agitation. And of course, you can close it in a nice glove box to achieve very good inner conditions. For instance, you can perform olefin polymerizations for very sensitive catalysts and so on. So basically, you need the right platform for more specialized chemistry. And some other variations commercially available nowadays, for instance, I already mentioned the microwave possibilities. Now they come up with some photopolymerizations, similar rate of parallel reactors, but now every reactor has a single UV light that you can achieve some photochemistry, right? Some disposable vials, if you are not very keen to wash the glass reactors I showed you before, basically just buy one of these ones, disposable vials. You can store your libraries or your samples here. And if you do a new experiment, basically you just take a new bag and perform it. Some small chemistry or small scale synthesis as well. You can go for libraries up to in the range of microliters, no? Let's say 100 microliters, like that. And so I will move a bit faster now due to the time. But what's next? No, I guess at this stage, I think we are very good in terms of doing polymerizations with an automated parallel synthesizers, I must say. Somehow we managed to follow the reactions, take samples to characterize the polymers, the materials, or to measure the kinetics somehow offline. So basically that means you prepare the sample of the reaction, take samples, put it somewhere in the vials, prepare these vials, and bring it to the characterization machine. So that works somehow fine, but of course, people are always keen to have faster results and more easily. So basically, people start to combine online characterization methods with these machines. And I mentioned a couple of examples in this sense. So in the past, our group combined the chemistry platforms together with some gas chromatography and GPC. So basically, the robot was capable to take the sample, put it in the injection port of the GC or the GPC, and run the analysis. Of course, you can run one sample once your first sample is finished. No? That's typically, let's say, 15 minutes in this case. So if you want to have an online analysis, you can process one sample every 15 minutes in this specific case. But some other researchers, for instance, Tanya Jonkers in Australia, in Monash, they decide to combine a flow reactor, put it online with a GPC, and basically everything what comes from the flow reactor goes to the GPC to determine the molar mass and provides feedback to a computer algorithm, and then back to the initial conditions of the reactor to achieve a very specific synthesis of polymers of a specific molar mass. No? This is a very nice example, for instance, of the online characterizations or real-time data. And of course, if you think a little bit more about the future, how the field is going to be developed, or where are we going? Of course, online characterization or real-time data is necessary to feed up some artificial intelligence or machine learning algorithms, no? That at the end of the day, we would like to have an autonomous lab that produces on demand a polymer that we want to investigate or to apply in different circumstances. It would be nice to have a machine that say, well, okay, I want a polymer with this molar mass, this viscosity, or this functionality, and the machine will run it for you automatically. But we are still far away from this. But well, let's say that the field is moving toward that direction. As a summary or not, look at some opportunities, of course, of the field. I'll show you this cycle, let's say, is the typical, sorry, the typical, I need to go back. Sorry for that. Something going wrong. Is here. So this is the typical cycle. Let's say for an R&D run by high-throughput. So you start with experimental design. Okay, how many polymers you want to build up, which variations, which composition, or which combinations. Then you have a synthesizer, which is automated or parallel. Right? That's, let's say that at that point we have more or less everything under control. So we can make polymers in these kind of machines with reproducible results and at some point also precise. But then you come with the bottlenecks, no? And this is really the state of the art where we are now in this field. Basically, we start to combine online characterization techniques to acquire the data more rapidly and analyze it faster, let's say. But we are still at the time that we need to prepare sample, bring it to a machine, wait for a couple of hours or days, analyze those results, and then make the next iteration. So we are working on this, but it's even worse when you think about purification of the libraries of the polymers. Of course, you make a library of, I don't know, 20, 40, 30 polymers, but then you want to investigate for some, I must say, biological applications. But of course, as it comes from the reactor, you cannot use the polymer. You need to purify it somehow, no? To remove the excess of monomer or solvent that most of the time are toxic for biological systems. So you need to precipitate or to dialyze one of each samples and then give it to the biologist to measure the properties. But honestly, that step is very manual nowadays. No? So we are working on developing new purification methods to achieve this. This is the bottleneck of the field. And it's together with the online characterization are two key components to run the cycle here more efficiently. No? So we still have to solve these problems until we really digitalize the synthesis of polymers. Well, one your polymer is pure, or you can evaluate it with different properties. You run different applications or methods to achieve to evaluate the property. So you make some conclusions or analyze the data. If you are happy with the results, then you finish. If not, you go back again to the next iteration. So let's say the bottlenecks are still the real-time data of the experiments and the purifications of the library. But I mean, researchers are moving in that direction. So the final goal of this field is, of course, to digitalize all the synthesis of polymers and generate sample or libraries that can be easily measured or applied. And with that, well, of course, I want to thank different people. Of course, this is the research of many years at different locations, different works. I cannot mention all the people who were really involved, but Simon was one of them. But of course, the funding comes from different countries and different agencies, as you can see in the screen. Some picture of the group I'm currently working on in Jena. We are always happy to have visitors in case you would like to have some stays or some visits, so we can welcome you here. And with that, I think I'm more or less on time, right? I want to thank you for your attention, and while you have any questions, please feel free to ask. Thank you.
Okay, thanks a lot, Carlos. Thanks for an interesting talk. So the floor is open for questions now. If you have questions, you can either just ask them directly through the Zoom meeting, unmute your microphone and ask the question, or you can type them into the Zoom group chat, or you can type them in the chat in the YouTube if you're watching on YouTube. So if I start off, so wondering how long does it take to set up just a typical reaction in terms of programming and everything like that?
Well, I would say, I mean, as I said, depends on the chemistry. Well, an ionic, basically, what you cannot avoid, and probably it's another aspect we have to look at as scientists, how to automate the purification of the chemicals. Right? There are some progress, but most of the time in an ionic, you spend a lot of time purifying the monomers or the solvents, and the experiment is running in half an hour, 1 hour. So in that sense, well, you can spend 3-4 days in purifying the starting materials, and then half an hour run. But in terms of the robot, once you are familiar with the software and the hardware and so on, it takes you maybe 1 hour, 2 hours to set up one experiment and achieve well, as many reactors as you have in the deck, right? To learn about the software and get familiar with this kind of platforms, you need probably a training of, I would say, between 1 or 2 months, something like that. But once you are a little bit familiar, it's very easy. You have some templates in the programs. You can just easily change the amounts of chemicals you want to add and the times you want to sample, or the different combinations you need. Yeah.
And then, so you talked a lot about high-throughput synthesis, and then towards the end of your talk, you kind of touched on some of the bottlenecks with purification and analysis.
Yeah.
I know it seems like most of the analysis techniques for polymers are really kind of sequential techniques like GPC or NMR, where you can have an auto-sampler, but you still need to run the samples one after another. I mean, are there any kind of parallel techniques or?
Yeah, exactly. Honestly, I think they are not still. I mean, we are implementing, for instance, a bench NMR nowadays in our labs. That you take a sample from the reactor, run it to a loop, goes through the NMR, and get the NMR. But it still takes, let's say 5-10 minutes. But again, it's one by one. Right? Mm-hmm. Similar story with the GPC. But there are some other methods. For instance, you can use Raman or infrared. So then you have probes in the reactors, and you take a spectra as often as you want. Right? But for that, let's say a little bit downside is that you have to have a probe for every single reactor, and that makes it very expensive, basically.
Yeah. Yeah. Because it seems to me that, like, to really unlock the potential of high throughput chemistry, we really need to kind of redesign polymerizations in a way, like in terms of maybe the way that polymerizations are set up to try and minimize the amount of purification you need to do, and the kinds of analysis that we do. I mean, perhaps we need to analyze different things. I don't know. I mean,
oh yeah, absolutely. I mean, that was part of the goal of one of the examples I showed, with these quasi blocks. Mm-hmm. It's just a way to get access to block copolymers in a faster way. Yeah. Even though they are not completely pure, but it also depends for what you want. You really need a pure block for your applications or your investigation. Then you cannot avoid it. No? You have to do in a very strict way. But if you are able just to live with a few defects in the second block, and let's say to still at least to get some trends how a material would behave in these compositions of blocks, would be okay. But yeah, it's a combination of well, compromise and what you can achieve, no, in these machines. And I mean, it's amazing how scientists or researchers come with different clever ideas, know how to circumvent some problems, no, and it's nice at some point. But yeah, the field is still in development. Of course, it would be nice to have a machine that you tell, okay, I need a block of polymer of this monomer with this and this composition and this molar mass, and you ask, and you come next morning, and here's your polymer. That would be great, actually. But we are still very far away from that.
Do you think, I mean, at the end of your talk, you mentioned machine learning a little bit. I mean, would that be kind of the goal of implementing machine learning, high throughput stuff?
Yeah, absolutely. I mean, some researchers are working on that. For instance, Tanya Jonkers in Monash, with this flow reactor, basically they tap the monomer, the molar mass of the monomer they would like to have. In this case, it's homopolymer. It's a nice example, but of course we still have to work on a more complex architectures or molecules. Then you type the molar mass of the monomer, so the machine start running and start learning, no, basically. So first it tests some conditions, evaluates the molar mass, goes to the second iteration, and perhaps varies the initiator or the RAFT agent, or whatever. Evaluate the second run and start learning, you know. So I'm getting closer to the molar mass I am targeting or far away, then I go back to the next experiment and vary. So that's nice. And in this publication, basically they show that for a specific example, they need 4 or 5 iterations to come to the target, right? So that's a good progress. But again, it's for a homopolymer is nice. So for a block of polymer, then you still need to, or we still need to think how to improve all these techniques. But this is a first step, like, basically, and that would be the goal, basically, that you tell your machine what you need and it does it itself without any help. Yeah.
Sounds ideal. Are there any other questions?
Mm-hmm. Let's say the short answer is, I would say, is yes. No, in our labs we specialize more to the batch reactors. I mainly show you in the presentation. But yeah, we do some flow chemistry. But I would say, well, I personally do a little bit of flow chemistry myself. But I have colleagues or collaborators that they focus more on these techniques. Let's say the advantage in these flow reactors or flow chemistry is that you can vary the conditions very quickly, right? Well, some people they have combined both basically, and it makes sense. I mean, you just number out the flow reactors basically, but you probably will progress faster in your results and your work. But what is also a matter of how much budget is available to build a more complex machine, let's say, and how many results you really need, no, for a certain project or goal. But there is no limitation. Basically, I guess you could use both in combination of both. Yeah. The nice with flow reactors is that the volumes are relatively small. Basically, you can change the conditions very quickly. Mhm. Yes. Mhm. Well, once for the machines we have in our labs, once you learn the software and the hardware, to set up, as I said to Simon, to set up an experiment takes you maybe 2 hours, 1 hour, depends how complex it is. And when it runs, well, it runs for, well, as long as you require the polymerization for us, typical examples are, I don't know, 8, 10 hours. The machine starts to take samples different times. Let's say next morning, when you come to the lab, you pick up the samples and bring it to the next machine. That will take you, I don't know, half an hour, 1 hour. And if you want to set up another experiment, you have to do some cleaning, let's say, for another hour, or conditioning again the reactor, and then another hour to set up a new experiment. No, not yet. Well, not in our case, but I know some labs, for instance, in Liverpool, in the UK, where they are working on something that's called autonomous laboratories. No? So there they have a room literally with a robot that walks somehow. So pick up the rack of vials from one table and bring it to the another table alone, basically, and put it in the, I don't know, in the NMR or GC or different characterization. Once it's finished the analysis, take up the rack again and put it back somewhere else to the next measurements. So yeah, well, this sounds very interesting, but I mean, in my opinion, it's a nice example for sure. It's very, very interesting to see these machines in action. But still, I think we still have a lot of work to do. For instance, when it comes to the purification, when you have to precipitate the polymer or to dialyze it, especially the precipitation of a polymer is pretty much an art, I would say. No, still. Yeah.
Okay.
Thanks.
So are there anyone else want to ask a question? So if not, then I'll say thanks a lot to Carlos. Thanks for your time and thanks for a great talk, and look forward to seeing you again soon.
Well, thank you. Thanks for the invitation, Simon, Etienne. Have a nice weekend, and nice weekend to everybody who was listening until the end. Bye-bye.
Thanks a lot. Goodbye.
Goodbye.